Okay, good morning, everyone, and welcome to the second lecture of Unicode's Machine Learning Summer School. I assume you can see my screen. If not, please type in the chat. Um, Today, we're going to be talking about two things primarily: naive Bayes and linear regression. Naive just sort of means simple, and naive Bayes is this very simple way of applying Bayes' theorem. I assume you are all familiar with Bayes' theorem, but I will at least walk through the basics for you. Um, but that said, like a lot of times I will walk through things for you, but that is no reason for you to not study it on your own. I didn't put naive Bayes in the reading because there is a lot more that you need to focus on in terms of linear models than naive Bayes. But at the same time, like you can go back and read it um, hereafter. So yeah, I don't want to give you more work than the bare minimum that you need to do, because a lot of you have other commitments in the summer and we don't want to waste your time. That said, let's start with naive Bayes and linear regression. So to start this lecture off, I want to tell you a story of this mysterious email thread. Um, Once upon a time, I got this email from someone, and that someone was called Mac Daniel. Max said he's an attorney representing the late engineer Michael A. Mehta, who died during the 2004 tsunami while on vacation with his family in Thailand. I should have started the lecture with a trigger warning. There is a discussion of probably fake death in this email thread. Sorry about that. He seems to be related to you, hence I've contacted you to discuss this matter with you. I have lost my cursor. I cannot admit new applicants, but the TAs are active, so thank you very much. So Mac Daniel tells me he is contacting me to discuss this matter with me. Of course, I write back. Hi, McDaniel. I'm terribly sorry to hear this. Michael was a dear surname sharer of my family. Please let me know how we can send him his family a card expressing our regret and asking if he left us anything in his will. We're very eager to make contact with the survivors 15 years after his death. Hope they're doing well. Right. So this happened in 2019, and Michael A. Mehta obviously passed away regretfully in 2004. So I talked to him for a while. Mac masterminded a plan. He said anyone I present to the bank is automatically the inheritor of the funds, although he obviously wanted some surname sharer like myself to avoid questioning from the bank in terms of this inheritance. And he will, of course, graciously handle everything on my behalf as my lawyer. And after the transfer, I take my 40% share, which is 2.8 million US dollars, and his share being 60% of 4.2 million US dollars, which is usually the case. The lawyer takes the lion's share of your inheritance. I could naturally not contain my excitement, and I immediately wrote back. I asked him if he wanted to plan some trips to Las Vegas. But more importantly, I asked him if I could provide my roommate or father's details instead, since my stars were not aligned. He clearly didn't seem to know the people that I thought he would know. And we continued talking for a while. Um, I sent him all the info from my guarantor, a particular Jacques Spiero, who lives in a particular building near me called Black Pearl of Juhu. He works on pirate equity, and his nationality is Indian, but he wants to settle in the UK. This is, of course, a real person. And I asked him if he can transfer the dead man's treasure to my relative. Mac doubted my integrity. It was not great. I really felt bad. And I was thinking about like what is going on, but clearly Mac thinks Mac thinks I'm scamming him, I guess. Um, and that was like more or less the end of the conversation. I was very upset. I wrote back to Big Mac, and um, I confess I lost my cool. Unfortunately, McDaniel did not write back, and I missed out on a chance to be a millionaire. But with the naive Bayes algorithm, the goal of this entire exercise is you should not miss out on a chance to be a millionaire, even though I may have lost it. So I started thinking about how to use machine learning to help us detect these kinds of messages and make us all millionaires. What I will say is naive Bayes is not really machine learning, but like, okay, early days, everything in statistics started to become machine learning. With that said, and with this nice, well, hopefully nice story that taught you all something, let's get into naive Bayes. So the first question someone wants to ask when they want to become millionaires are, what do potential millionaires like Mac talk about? And I started taking a stock market investment course because that's clearly the way to become a millionaire, to learn about this. I started getting some spam emails, or more importantly, the title should have been How Not to Become a Millionaire, because that's really what spam email teaches you to do, or taught me to do. Um, a, a couple of emails I got after the stock market course started looking like this. These are all the titles. You can be a millionaire today using these 5 simple tricks. You must invest in this company today. You have guaranteed profit from top stock tips. 3 secrets to mint millions. This 2-minute video teaches you to be just like a millionaire. And if you start looking at these titles, you might start noticing some similarities, some sorts of words that have color coded to give you an idea of like what we're trying to go for here. And assume that you have some emails. Like, I've taken this course, I've gotten a lot of emails, and I've filtered them based on whether they're relevant to me or not. And I want to basically build an algorithm that can tell me if a new email is spam or ham. Ham is just non-spam, but people use this spam ham terminology. Um, so yeah, so the question then is, we know that if the email is spam, it probably has certain types of words in it. So if a new email, and this one, suppose it's from my course instructor for the stock market course, it says lecture 8, how to invest like a millionaire. The question we're trying to answer is, should it be spam? And I'm not going to spoil that. That answer is for you to determine. But the key assumption we start by making for this naive Bayes algorithm are that words occur independently of each other given the label of the documents. And what does this mean? What this means is, we're saying words um, are like words are like coin flips. When you flip a coin once, you may get heads or tails. That has no bearing on the second coin flip that you perform right after, which is a um, actually, I should pause and ask you a question here. Is this a fair assumption to make? You can chat, you can raise your hand. Let me bring back my cursor to the screen. I feel like all my professors in this moment struggling to understand technology. I see now what happened. No, okay. So it's clear to a lot of people that this is absolutely not a fair assumption to make. You're right. Um, Typically, words form sentences, and we try to string together coherent sounding sets of words to form a sentence. And just because we sample this assumption of independence or conditional independence does not make sense, because words are not independent of each other. However, this independence assumption allows us to build this algorithm in like a very simple way, and we will make this assumption anyway. So like, word of advice in machine learning, whenever someone gives you an algorithm, first ask them, what assumptions are you making? Check if those assumptions make sense with respect to the data that you're working with. And then go back and say, okay, if I've made this assumption, is there a better assumption I can make? Typically, better assumptions are weaker assumptions. So a slightly weaker assumption might be sentences are independent, like conditionally independent, given spam, which is just saying like groups of words might be related, but like, um, um, yeah, it's less strong than saying, oh, every word is independent. So Weaker assumptions are better because they give you more flexibility. Stronger assumptions are not as great unless you know what you're doing. So yeah, generally that's the way progress is made. You build an algorithm with some very strong assumptions, then you slightly relax it, build a more general version of the algorithm, relax it further, build a more general version, and go on from there. So spam classification via Bayes rule. The question we're asking is, again, going back to the previous slide. Can I click this question? Yes. So given conditional on an email being spam, we know that these are the words that it uses. Now, conditional on the words that it uses, can we classify whether it is spam or not? And if you're familiar with Bayes rule, which is, well, I'm not going to get into Bayes rule. Maybe I'm sorry, I lied to you. Bayes rule is telling you, okay, let's get into it. I feel a bit guilty about this. Start broadcast. Yes, let's start screen sharing. So what we're saying is Bayes rule really quickly told us if we have, oh, yeah, I'm sharing. Okay. If we have P of X given Y, this is the same as P of Y given X times P of X upon P of Y. Why is this the case? Well, if you remember, and I'm writing down the proof for this, if you remember, the joint probability of X and Y can be decomposed as the conditional probability of X given Y times the marginal probability of Y. If anyone has a question about this, now is a good time to pause, raise your hand and ask me. Cool. So this is fair, but you can also write this as P of Y given X times P of X, right? There is no reason this is not the case. So now that we have these, if you equate LHS and RHS, P of X given Y times P of Y equal to P of Y given X times P of X. And this Y goes down and you arrive at this formulation. So that was Bayes rule. Couple of, it's not super important right now, but this is, we'll get to priors posteriors later. This is all you need to know for now. This is how we derive Bayes rule. Super simple. But now that we have X and Y, we replace with words given spam. Or the question we're asking is it spam given some words in its header? This is equal to P of words given spam times conditional probability of words given spam times marginal probability of spam on marginal probability of words. So I should really write words here because it's not WI, it's set of all the words. And where basically the conditional independence assumption we made allows us to say this is equal to product over I of, sorry, this is not this. The assumption we made allows us to say that words are independent conditional on spam, right? So this will then be equal to product of all the words I given spam. That's all that people are trying to say. So if you have a question, I'll pause for a minute and let you ask me questions. Cool. And let's get back to the screen. Okay, where are we? Yeah. So yeah, so this is the question. This is the math. It's a simple question we're asking. And the goal that we want to the goal of what we want to do is, okay, so one thing that you might see here is where is the denominator, but where is the marginal probability of the words? Well, it's more of a normalizing constant. So the P of W that was in the denominator, we basically remove it and say that this is proportional to these things. We'll get it back later and we'll write the proper mathematical equation, but that's the reason it's missing out here. Yeah, that's all I want to say. So hopefully at least the general idea is clear to you. We use Bayes rule in a very simple way. That's why it's called the naive Bayes algorithm. This is how we represent this conditional independence. And this is a graphical model. It is saying the exact same thing that we said, where we said P of, can I annotate? From the iPad. Oh, cool, I can. This is saying the same thing as P of W words given span is equal to product overall words of P of Wi given span. And bear in mind that this, I didn't say this explicitly, but this is W1, W2, Wn given span. So you're just decomposing the joint as a product of marginals because of conditional independence. I will repeat that. You're decomposing the joint as a product of marginals due to conditional independence. The joint is the joint probability of the words conditional on spam, which I probably shouldn't call joint to confuse you. I should call it the conditional probability of words given spam. But in either case, hopefully you follow this. This is the diagrammatic representation. These arrows represent that it is only dependent on spam and it is not dependent on the words before it, which is wrong. In real life, there would be this arrow, right? The word coming after is dependent on the word coming before it. And a lot of you might already be aware of sequence to sequence models. And this is a sequence, like it's a sequence of words. So we're making the wrong assumption because we're removing these arrows. So still, it's an assumption. It's a strong assumption, but it helps us build this algorithm. So why not? Okay, let's clear my screen and move on. So that is the naive Bayes algorithm. It's written in the next slide. This is plate notation. It's super important because oftentimes when you're describing models, you don't want to sit and write out every assumption you make. This basically encapsulates this diagram, encapsulates all of what we said before. So the conditional independence, the joint decomposing into a product of marginals, all of that can be represented with this one diagram. So it's important for you to know about these things. We won't be using them, but you will come across them, especially when you come to graphical models and generative models and papers like that. Cool. So the question now is how to estimate this probability of word given spam. Does anyone have an answer for this? If I give you a bunch of email, sorry, myself. Okay, we have one answer, use maximum likelihood. Estimate directly from data given a classification. This is fair. Um, to so I didn't understand maximum likelihood when I was an undergrad, and if someone said that, I would just be confused out of my mind. So I'm going to boil down what is being said here. You count the number of words occurring in these spam emails. That's it. Um, if you know which ones are spam, which ones are ham, just sit down and count the number of times millionaires occur, the number of times invest whatever occurs, the number of times it's like 3 smart tricks, 2 smart tricks. Exactly. Count spammy words in a data set of emails for each word of interest. And that's it. Like people again use terminology which is super important. Um, and yeah, that's basically what this equation is saying. And one thing Smola mentions in his lecture is super important is you have to think about metadata with just using the titles of the emails for now. These are just email titles. They're not the content. They're not when the email was sent. There are like a number of things you have to filter, um, which is saying that, look, this email comes from someone from somewhere doing something at some time. You can use all of those things to filter spam or ham. But right now, we're just talking about headers and we're talking about counting words. So going back to where we were, there are a number of things that you can use to send like figure out what more can you use to filter spam or not. We're not going to get into that, but it's important to know that that's possible. This slide is basically
Swapnil,
yeah. Go ahead.
sorry to disturb you, but I think we have a doubt on chat. They
Oh,
didn't
cool.
understand the previous slide.
The previous slide.
The doubt is that why W1 and spam, W2 spam are independent. Is that an assumption?
Yeah, so that was we spent a bit of time discussing that. It was about this conditional independence of words. So millionaire occurring in a spam email will be independent of investment occurring in a spam email. We're saying, and if you watch Smola's video, this is he explains very clearly that what this assumption says is the spammer has a keyboard where each key corresponds to a word, and he arbitrarily presses some keys to compose an email. There is no relationship between the sequence of keys he presses. That's what we're saying. That's also what we said here, where we said the assumption is that this arrow, I should change my color. This arrow does not exist, which is not the right assumption because in a word, if you have my cat ate cat food, there is some relationship between cat ate cat food. Um, there is a certain ownership relation between my cat. There's a certain, I don't know. I mean, if you have a cat, you call it cat food. If you have a dog, you call it dog food. If you're a horse, you call it carrots. I don't know. But there is a certain relationship between words that results in this being a whole sequence and not independently drawn words, which is why we said that this assumption is wrong, but we still make this assumption because it allows us to build a really simple algorithm and boil this problem down to something that's really easily solvable. So if that was your question, let me know if that answers your question or if you want me to expand on that.
Yeah, it's solved. The person wrote that it's done.
Gotcha. Thanks a lot. In a way, that assumption makes sense. Say these emails are all computer generated. To a computer, the coherence of a sentence means nothing. Sure, if the email was computer generated, it depends on the generation procedure. So you can assume that the computer generates it in a way that you without these arrows. But in today's time, with all of these sequence to sequence models becoming so popular, it's unlikely that a computer would just use independent samples of words. Um, Also, who sits and builds these sorts of dictionaries anyway? Um, but yeah, like if you see an email that has a really badly formed title, you're not going to really open it. So again, lots of reasons for that to be a bad assumption. um, you I would think it's incredibly hard to justify that being correct, but I like that you're trying. Keep it up. Cool. So going back to where we were, yes. What are these things saying? This n of I and y upon n of y is just saying the occurrence of word I in a spam email. Let me annotate so you can see it. This is what I'm talking about. This is what the counting referred to. And this is what the number of spam emails refers to. So the probability of an email being spam. That's it. The number of times we have a spam email upon total number of emails. The number of times a word occurs in a spam email versus the total number of spam emails. That's all. We're calculating these probabilities, and the same formula that we used earlier, except now we replace the terms with the probabilities. And like we discussed, we decompose the joint. We decompose the joint as the product of marginals. So, okay, remove this so you can see the screen better. Evidently, I can't clear the screen. What is going on? Let's do this. Annotate, clear. Cool. Share again. Stop one and play. Okay. Anyone with any doubts about what I'm saying here? We're basically calculating the things we just discussed, plugging them into an equation, and getting the output as the probability of spam given words. Again, bear in mind, we are not looking at the denominator right now. There's a proportionality sign. The denominator is a proportionality constant, which will allow us to turn this proportionality into equal to, but that comes later. Right now, we're still just looking at P of y given x is proportional to P of x given y times P of y. Cool. I'm going to assume everyone is good with this and move to the next slide. Before we go there, I think an important question needs to be asked. Can someone guess where this might go wrong in terms of, sure, we're making some assumptions. Let's assume that that's one major issue with this. Okay. Now in this entire idea of counting these things to get the probabilities, so we're counting how many times the word occurs, we're counting how many times a particular spam email occurs. Can you think about what might be going wrong here? And because this is a kind of a hard question, I can hint at it.
Wait, I have a question. So if two words are classified as spam and or ham, corresponding to some email, so would that hamper the performance of the classifier?
When you say two words, can you clarify what you mean? Two words are classified.
Sorry. I'm sorry. Only a word, for suppose say trick, is both in many emails that we have in our database, and which might relate to spam or a non-spam email.
So equal probability of spam and equal probability of non-spam.
For that word being in email.
Yeah, so that word doesn't help us decide spam or ham.
Oh, okay, cool.
Yeah, you would add more weight to the rest of the words, right?
Hello.
Yeah.
Can you
Yeah,
hear me?
I
Okay.
can hear you. There's a lot of background noise, but I can repeat the answer you sent to me, which seems to be reasonable. So Vinayak says if a word in test data is not found in training data, then we might run into a lot of problems. And this is important. If I never see the word billionaire in my training data, but billionaire is uh, present in almost all of the spam emails for the test data, then I have never learned to guess that if there is billionaire, then this is spam. If the spammer changes the spelling of the word, this is an excellent point. Yes, that could create a lot of issues, but in general, this ties to training versus test. So it is essentially the same point that this word in test data is spammy, but in training data, we've never encountered it, so we don't know what to say. So yeah, that there are issues with this naive Bayes approach, and we need to account for those things. So one thing you could do is continuously train an algorithm with new incoming spam emails. Some other things you could do is like split your training set in different ways. There are these cross validation approaches where you don't just need to split your data once into train and test. You can split it into different sets of train and test in a certain way, so as to not leak your test data. But anyway, um, a question in the chat seems to be, is the opposite true? Like we can't teach our classifier the importance of context. The word invest could actually be about investment advice. Well, in this classifier, we're not looking at context because of this conditional independence assumption, but you are right that you should think of like, how do we, and you're already doing that. Like research evolved by thinking of, okay, what if we do groups of words? What if like we do one word on each side as context, then we do two words on each side as context. There are these n, I forget the exact term for some reason.
Ngram.
N-gram models. Yeah. So the idea emerged from these kinds of thoughts that some people had, which was like, well, we're only using one word. What if we use two? What if we use three? What if we use four at a time? And then in the limit that went up to, okay, what if we like place a probability, and as the word gets further away, we consider it less and less, but we never discard the rest of the sentence, and so on and so forth. But yeah, this is very like, these are all excellent points about like how people, where people started and where it went from there. But you realize that in order to start the exact thing that I mentioned earlier, you need to make a really strong assumption and solve a problem, and then relax it and solve more general problems. Cool. So we discussed 2 points, and this is the mathematical version of it. What if a certain feature does not appear in the spam email classification in the training data at all? And what if a certain feature appears all the time, and we don't know, or equal numbers of times, and we don't know what to say about it? Yeah. So with that, well, there are some approaches to solve this. So I will mention that in case a word doesn't, like, you can assume like you can add a minimum number to all of these word probabilities just to ensure that there are no zeros. So this n(i)y equal to 0 is not a major issue, because while it may appear on the test set, but it also now has a non-zero training probability. So at least you're going to learn something with it wherever it appears in the training set. At least it's not zero. Yeah, I will leave this to you to think about, just because I feel like it's a good slide to spend some time on. Just in terms of, we discussed this already. There we have the chat. I can, the chat is usually saved. I can share them. Anyway, the point being, we have the recording. You can look at what we discussed here, what these terms represent, and what these assumptions are formalized as mathematically. I would highly recommend that, just because like I spent a lot of time on that. I think it is important to realize like, oh, this fails, but this is how we express it, and this is how we address it. If nothing, watch Mola's video. He discusses all of this anyway. And then with that, we get to the simple algorithm. We already discussed most of this. We already discussed all of this. For each document word pair, you want to do aggregate the label counts, count the number of occurrences of the word for each feature, then estimate the distribution, which is the number of spam emails. Then for each pair, do the conditional, estimate the conditional distribution. Using these conditional distributions, compute the probability of spam given words times these things. Yeah, we've been over this, but I'll still pause here. You don't have to worry about what all of these terms mean right now. I'll pull an Andrew Ng on you and say, don't worry about this. This is fine. We'll come up with models and these distributions later. What I'm talking about, sorry, my cursor was not on. What I'm talking about is this Parson windows, exponential family, mixture models. Estimate this distribution is, it's fine. It's telling you figure out what shape this fits into best. And by shape, I mean class of models. So some are bell-shaped curves, some are flat lines, some are weird looking curves with some parameters. And you just want to estimate which one this fits into because that gives you certain properties. But it's not relevant right now. Like it's not super important for you to focus on that part. What you're just looking at is Bayes rule, how you apply it. And yeah, before I go to the next slide, I'll pause. We are 45 minutes into the lecture and we have linear models left. I'm not seeing any questions, so I will point you to a real world example of how Smola applies naive Bayes. I'll also like explain to you sort of what he's doing because I'm pretty sure it will be confusing because he works with image data. We haven't discussed image data yet. So watch this video, but I'll tell you what is happening in the video. Essentially, let's go with this. An image, the MNIST is like this image of digits. One, this is also one. And it's basically a 0, 1 set of images. So all the pixels that are not 1 are 0. Sorry, that's a bad terminology to use. Pixels can have a value of 0 or 1. All the pixels that represent this image are ones, whereas all the pixels that do not represent this image take the value of zeros. Maybe I should start with an example of 2 instead of 1 because that might be confusing. So there are different images of 2s in this data set that we have. 2 of them might look like this, and this is 28 cross 28 pixels, which is equal to a total of 784 pixels. Each pixel is either 0 or 1. These pixels are ones, for example. These pixels are zeros because they don't represent the image. That's what I mean. Hopefully this is clear. The way we work with this data is we blow it up row-wise. So we create a whole big row of 784 values. So this corresponds to this array of 0, 1, 1, 0. So this is one row, this is another row, this is a third row. Hopefully you understand. So in the third row, the 5th element is 1, 6th element is 1, 7th element is 0, 0, 0. Again, I'm being very, very, like, I'm explaining this as if it were a 5-year-old for the benefit of those who never worked with images. Typically images are RGB. So this is actually not a one, but like a set of 3 values, 250 from 0 to 255. So it can be like this, but we're just taking a very simple representation. We're saying this is just either 1 or it is 0. Yeah. So this is image data. What he does with this is you count your pixel values. These are your words. Well, your pixels are your words. You shouldn't say pixel values. What he does is he counts. So he overlays all of these images and he counts, like, okay, at this location in this 2, at this location in this first example, there was 0, 1, 1, 0. In this example, it was 0, 1, 1, 1. And so you like sum this up for example 1, example 2, or I should say sample 1, sample 2 of data. And you basically calculate on average, or for these 2s, what is the probability? I shouldn't have started with on average. You calculate for the label 2, like the number 2 in this image. Will this pixel have a value of 1 or 0, and the particular probabilities of that? And when a new image comes in, now you have the pixel values and you want to go back and say, what is the probability of 2? So yeah, that's essentially what this algorithm does. So for, instead of the spam words conditional on spam, it is pixel value condition on labels. And now it is multiple labels. So it's not just spam on non-spam. It is either the number 0, either the number 1, either the number 2, up to the number 9. So for each number, you calculate the pixel probabilities conditional on that label. And then when a new image comes in, you have the pixel values and you want to calculate what label is this conditional on the pixel values. That is the application that is discussed in the video that I shared. I don't know, you haven't watched this video, so I will pause if you have questions about what I just showed you. And you can go back and watch the example later. Okay, I'm assuming there's no questions about that. If there are, you can still stop me. I'll give you a 5 to 7 minute, let's say 10-minute break. Okay, there's a question. But can't the 2 be like towards the right side of the training set, or all 2 in the center? No, that's an excellent question. 2 does not need to be on the right side, or does not need to be in the center. That is why we're taking the pixel probabilities. So for that 2, okay, let's go back to screen sharing. So if I have a 2 that is like this, you are right that these pixels will now all be zeros. So it might be something like 0, 0, 0, 0, 0. And then somewhere here, there are some ones and zeros. But that is exactly why we are summing and we're calculating the probabilities. We're counting, like, this pixel for this image is 1, sure. But most of the other images, it is 0. So when you get a test sample, you're still going to say, well, I have barely ever seen an example like this, so low probability of it being 2. But yeah, that's a great question, and that's the price you pay for making this assumption. On the other hand, if you had used the sequence of pixels to figure out if it was 2 or not, then the sequence still remains constant regardless of where the image is taken from. And then there are other strategies of like centering this image before actually going about this training process and all of those things. But those are this is a great question, and like this comes up a lot when you talk about image analysis. Like, what if my object is in the corner? What if my object is here? That those are all the reasons. What if my object is rotated? Those are all the motivations. Again, we started with a very simple case, and we're going out and asking more important questions to make our algorithm more general. So then you have these data augmentations. Like, what if I just use some reverse tools to train this algorithm? What happens then? Because my test data might have some rotated images. Someone somewhere scanned a 2 upside down. But then the question is this a 5 or is this a 2? And anyway, important cases come up, but it starts with the important question that you asked, like, what if my 2 is on the side? Yes, sure, it can be on the side. The probabilities will be updated accordingly. If it's an important enough case, you want to oversample that sort of 2. So you want to create more artificial samples in your data set that are similar to that too. Those kinds of practices are related to, I don't know if data augmentation, but I would say, yeah, that's that kind of thing. But great question. Thank you for asking. Any others? Deep gave you an example of how a digit looks. Is that, yeah, how a digit looks. Great example. Thank you. It's in the chat. You should look it up. And with that, I will take a 10-minute break. Yeah, I'll be back in 5 minutes to answer questions, but I'll start off the recording after 10 minutes. So we still have 5 minutes. I'm just taking questions. There are 2 questions I saw. So the first one is, for each label, we can get a vector in R784. Yes. R784 is real dimension, real space with a 784 dimensional vector, basically. So it is important that you know this terminology, because firstly, for publications, you need to write fancy terms. I was just talking to my friend yesterday and I was saying, you need to, max is not cool enough. You need to write L infinity norm of a vector, which is the same thing as taking max of a vector. But L infinity norm sounds so much more hyped and cooler than taking the max. I think that's correct. Anyway, back to the point. So for a new test image, we will convert it into a vector. Yes, we will. Can we find the distance between the test vector and each label vector? Will it give any good result? What you are describing is exactly what people do for clustering. They cluster. So you want to think about this as, I want one candidate for 2 that represents all of the things that happen in 2. And then I want to find the distance of this average 2 with a new test 2. And if test 2 falls into average 2, then update the average 2, include the test 2. Not that's more of an online setting where you keep updating your average candidates with new data. But just test is just calculating the distance between this average 2 and a new 2, and then calculating new 2 versus 0, new 2 versus 1, new 2 versus 2, versus 3, 4, 5, 6, 7, 8, 9. Anyway, hopefully that was clear. Yes, it will give a good result because this is the clustering algorithm and it works. Yeah, I mean, clustering works. At least for this case, I can say with confidence that this will give you a good answer. It just depends on your training data. If you have a good representative sample of 2s and you have another 2 that looks more or less similar to those, then it will give you a good result. If you have this case of 5 and 2, which look very similar to each other, 5 and inverted 2, assuming you care about inverted 2s. So case based on the case, the general algorithm works. The specific example is up to you. Second question. So is the probability of each pixel taken, how is the idea extended to 2D data? Again, excellent question. The stupid way of going about this is to increase the length of that vector. Like, you can always dump any number of dimensional tensor, 5-dimensional tensor into 1 dimension, just very, very long. So the stupid way of going about this is by doing that. There are better ways, but they're more complicated, obviously. So I'm not necessarily going to get into that, but you can do it dimension wise if you care about that. You're still doing it dimension wise by dumping it into a vector, but it just, you might want to weight certain dimensions more than other dimensions. So a match in the first dimension is not necessarily great, but a match in the third dimension might be super important for your use case. So that's yeah. Another question, are those numbers we see in CAPTCHA check in sites like IRCTC examples where algorithms don't get it right? There was this article I read about how Google was using us to transcribe, Google Books was a thing, and they were using CAPTCHA to transcribe books into real things, but I'm not sure how plausible that was. Like, I don't know the answer to your question. It seems to me that you would want that. So the question is, are CAPTCHAs created such that algorithms can't get it right? Yes, that is the intention, that an algorithm should not be able to solve CAPTCHA, but all CAPTCHAs so far, to my knowledge, have been broken by algorithms already. So there was CAPTCHA, CAPTCHA 2, CAPTCHA 3, reCAPTCHA, something like that. And I think all of them have been solved by algorithms. People have shown that. So yeah, you want that, but I don't know if you have that. Okay, with that said, we are back. And we are going to now discuss linear models for a while. I will try to end before time just so you have enough. I feel like you have enough fodder to spend on more things. And I have a couple of videos as recommendations to watch about linear models, in the sense, like, we will go through all of these things, but there is a lot more that can be said about linear models. Like 1 hour is not sufficient. Entire fields of study are dedicated to linear models and like interpreting them and using them for different use cases, discussing the assumptions made in linear models. And so I'll go through those, but for those of you who are interested, I will also give you additional resources. So let's start with linear models. As you might imagine, the first thing that comes to most people's heads when you say linear is a line. And as an example here, if you have 2 points, 0, 4 and 6, 0, the linear model that fits both these points is the line that passes through both of them, which is 2x plus 3y is equal to 12. And typically I will be talking in the, I forget what form this is called, the y is equal to mx plus c. But yeah, in high school geometry, there was a particular form that this was called, but I'm just going to use that form typically to say y is equal to mx plus c. We want to determine this m that tells us how to fit this x to the points that we have. A lot of times the points that we have do not lie in a straight line. So then which is the best line that passes on average closest to these points? And that is the entire point of linear models, that you have some data, you want to fit a linear model through it, but there is no model that perfectly fits all of this data. So you guess like which is the closest one that works out. You can obviously take a very complicated curve and fit it through every point, but that is probably not going to be like a general enough. Like when you have a new point, that curve is probably going to say something very weird about that point. And so that's part of the reason why people want linear models, is they're like, the true model might be more complicated, but at least this is simple enough for me to understand. By the true model, okay, so this goes back into like, what assumptions do we make in linear regression? So the first thing, when you're applying linear models to a problem, you are saying there is a certain true model that generated this data. Our goal is to fit these points and discover that true model, right? This is not just true for linear models. Like in any sort of function approximator, neural networks are a function approximator because they map a set of inputs to a set of outputs. That is what a function does. It takes some inputs, gives you some outputs. So any sort of function approximator is essentially trying to discover this true function that maps these inputs to all of these outputs perfectly. We assume that there is some unknown true function. And what we're doing is trying to estimate it. That's why it's called an estimator. What are you estimating? The true function. Why is there a true function? That's a philosophical question. Why is there order, or is the world completely chaotic and we cannot do anything? If there is no order in the world, then we cannot discover anything. If there are no patterns, then what can you discover? Everything is random. And like I said, that's a philosophical argument to make. But in general, if you say that there is structure in the world, slope intercept form. Yes, y is equal to mx plus c is called the slope intercept form. Thank you very much. You're sending me direct messages, but you can always post on public chat. Like, don't feel embarrassed about this. I have made a lot of mistakes. You can make it. You are free to make mistakes. Cool. But no pressure. Back to what I was saying. What was I saying? Someone please post in chat what I was saying. This is why you should not have chat open when you're teaching. Right, I was talking about curve fitting and points and linear models, and this assumption that there is some true data generating process and that we're trying to estimate this data generating process with our class of models. With that, let's jump into linear models with a practical problem. House buying 101. So at least in the US, this is how house pricing works, right? Someone asks for some amount of money, you never give them that amount of money. And I think this is in general, not just the US. You always bargain, you negotiate because you can. And then you make a certain bid for a particular house, right? How you make the bid is entirely up to you. What we're assuming here is like, okay, there is some rational person, he sees some factors about the house, uses these factors to estimate a cost. There might be some true cost to the house, but what you need to bid is just like what is an amount that's firstly you can pay, secondly you think is fair, thirdly is not more than the amount they're asking for. That would be stupid for a number of obvious reasons. So the problem then is like estimating this price and estimating the bid you want to make. There are some websites, at least in the US, there is Zillow that estimates these things for you. So Zillow itself uses some artificial intelligence now. And this was very prominent. Like this happened recently where Zillow said, hey, we're going to use AI to discover house prices. And a variety of people said this is not a great idea because now you can actually game the system. So suppose you put up some really pretty photoshopped pictures and like you falsify some minor details. Turns out in front of your house, if you have this, I don't know what it's called, but you have your family name on it and you have the house number. Turns out if that font is really fancy, the house price goes up. So it's really arbitrary how these deep neural networks will work, but that's just a tidbit for you to think about. What we're doing here is applying a very simple linear model. So we have some features, we have the properties of the house, we have some features about the house, the number of bedrooms, the garages, the whatever, video data, the number of bedrooms, all of these things. And what we want to say is here is what we want to say, ignore the slides. What we want to say is just here is an estimate based on the features I saw. How do we want to say this? Well, we want to give a coefficient to each feature. If there are 7 bedrooms, increase price by 7 times $5,000. It's very cheap, but $50,000. So $350,000. If there are 20 windows in the house, I want to increase price by $5,000 per window. It's another $100,000. If the house is located in a certain area, I want to associate an area-wise base price to that house. So that all depends on this coefficient that you multiply this feature by. So in a linear model, you might think y is equal to m1 x1 plus m2 x2 plus m3 x3, which are just components of the slope for every component of your x. So you're just decomposing mx into m1 x1 plus m2 x2 plus m3 x3, and so on. Seems straightforward enough for me to not focus on that anymore. Go back to the slides and talk about the difference. Like we said, there is a certain listing price from the agent. There is a certain predicted sale price, which is typically less than the listed price, because why would you ask for less money than your house is worth, right? Yeah, this is highlighting the same thing. Like you can use historical data on price estimation. You don't want to overpay. Not crazy important. This is what I was talking about. Y is equal to W1 x1 plus W2 x2 plus W3 x3. Can I? Because my cursor is not around, I just want to annotate this thing for you. This is exactly what a linear model is. Can someone tell me if I add a W4 x3 square, is this still a linear model? Yes, it is
Yes, it is.
polynomial, but in the feature. It is not polynomial in the number of parameters. Typically, and this is a big source of confusion for a lot of people, at least it was for me when I started out. I was like, well, but it's not linear. Well, yes, but the models are not supposed to be linear in the features. The models are supposed to be linear in the parameters, and the W's are the parameters. The X's are just the features. So you can create arbitrary features and fit the models. It's still going to be a linear model as long as you consider it linear in the parameters. So as long as there is not a x3 raised to w5, this is still a linear model. Oh, sorry, as long as this is not the case, it is still a linear model, right? If you add this in, it clearly becomes non-linear because now there is a w5 term that is an exponent. Anyway, that was an important point to drive home. What do I want to? Yeah, another point I wanted to say was this is equivalent to like why typically when I started, I said, linear models, you think of lines, but curves are also linear models. It's just linear in the parameters. It can be non-linear in the features. That's fine. So that can be x5 times x6. This is fine. This is still a linear model as long as there is a W6 term here. Let's erase this for clarity. Yeah. So anyway, that hopefully that point was clear to you. And so we call this weights and biases. This is a W2, W3, B. Can someone tell me why there is a need for a bias term? One guess is noise in data. Otherwise, you're forced to go through the origin, noise in data, regularization. Values need not be centered around 0. Cases where all parameters are 0. Bias is like a base price, case in which all features are 0. Yeah, most of these answers are correct. It's basically like you want to add an offset element. Why do you want to add an offset element? Well, if for the features you consider, if there are 0 bedrooms, if it's in a very shitty area, if there are no fountains, it's still a house. It still will have some price. And in the other case also, like if you don't value all of these things, like you don't care about the number of bedrooms, you don't care about what area it is, and you don't care about the number of fountains, it's still a house, it still has to have some value. So regardless of whether features are zero, whether parameters are zero, there has to be some base price to the house, and that's essentially what we're saying. It's equivalent to saying does not pass through the origin. So geometrically, you want to fit a line that goes anywhere here, 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 here. With the bias, without this bias term, your line will typically go from here. But I don't know if I'm saying that right exactly. Hopefully you got the idea. Okay. Yeah, I think I said that right. So yeah, so weights and biases are determined later. Cool. There was a question, maybe. No, I don't see a question again. Cool. So
Yeah,
let's.
there was a question. So the question was that for every parameter, for each feature, there must only be one associated weight.
Yeah, that was. Yes, in this case, we are making that claim that for each feature there will be a parameter. If you're saying that if you're saying that there is a wn plus 1 xn, then all you're going to end up doing is like splitting this wn plus 1 times xn, and this could just be a new wn plus 2. So you're essentially doing the same thing. If you split, there is no sense in splitting one feature into two coefficients. Like, again, if you have an argument to make there, I'm happy to listen. But I think this was all I wanted to say. Got it. Cool. Okay, so we assumed, we didn't assume, we have some n-dimensional input, x, which are all these features about a house. The model has n-dimensional weights and a certain bias term. The output is a weighted sum of the inputs. In a vectorized form, you write that as this is a bracket notation. This is how you write vector multiplications. Dot product. Yeah, we've already been over this. I don't think I want to spend more time on this.
Swapnil, we have one more question in the chat.
Go ahead.
So the question is there a known approach for justifying xn versus xn square or sine of xn? So why we use xn in place of xn square or sine xn?
Why we use xn instead of xn square? I'm not sure I get the question. Like, we are multiplying two vectors. Are you saying a transformation of this vector?
Yeah. So we can transform the data however we would like. And so I want to know if there is a good justification for saying taking a particular column of your data set and squaring it, or taking the sine bits or anything along those lines. Does that make sense?
Yeah. So for some features, you might want to create a version of it where it is sine of xn and then fit that feature to data. For instance, if you believe that if you believe that house price scales exponentially with this number of bedrooms, then I guess you don't need to, but you could still create a bedroom squared feature and add that into your set of features that you're fitting your model to, and then you have a clear relationship between squared bedrooms and house price. I have the reason I'm hesitant is because like there's a whole discussion we had about like whether you should transform x and y, and I don't know if that is relevant to this, but I feel like that would be interesting for you to sit and listen to. This was in a separate video series, so I can link you to that later. Please remind me at the end of the call, because that was yeah. So usually it helps to know something about the data set to have a transformation. Particularly, there is a whole discussion about like again, not answering your question, but a related discussion on like some features might be correlated. You might want to drop some features, transform other features, and do stuff before you go about the fitting. But yeah, that the simplest explanation for your question is we assume that there aren't like problems such that we would need to transform the features, and we assume that we're not gaining anything by transforming the features in this very simple case. But you're right that in some problems where we know some relationships, like if you're fitting a force model, you know that force is proportional to what was no sorry if you're fitting a potential energy, no, yikes, if you're putting a kinetic energy model and you have kinetic energy is equal to half mv square, that is a known relationship, then you would ideally want a v squared feature, and then you can just regress that on all of the data that you have. So you can directly fit it as opposed to like fitting a feature that sort of varies in a weird way. Again, that was a very hand wavy explanation, but hopefully I motivated why you would want a transformation by knowing a bit more about the data. Well, this is a good question, and remind me to link you to that video again.
Sure, that definitely helped me, so thank you.
For sure. Cool. So we went into the vectorized version of this, and I don't want to get into neural networks right now, but essentially this is what you're doing for a single layered network, where you're multiplying your x's with some weights, adding some biases, and getting an output. The motivation for this is just, okay, I have 35-ish minutes left. Not bad. Maybe we have time to come back to this. Just a side note that neural networks derive from neuroscience, which in this case, it's just like 10th grade biology. I don't know if I had this in 10th grade biology. I assume people have had to study this. There is a neuron has certain parts. There is a certain information processing. There is a certain information transfer, and there is a certain connection to other neurons. So this is just like the same description, except like mathematically. So if you want to model a neuron, then this is how you do it. There is a computation center, there is an output, and there is a connection to the next layer. Not important at all right now. We'll get back to this at some point when you're studying deep neural networks and like advances and how those advances derive from biology. Cool. So now that we've estimated some price for the house, the next question is this the right estimate? And given that we have some data set, again, we can calculate instead of just guessing whether this is the right price. We can calculate like, okay, if I guess the price for this house that I know is already sold at a certain price, how far off am I? And this motivates the idea of a loss function. A loss function typically tells you how good or bad you are. In this case, how bad your classifier is, because the higher the loss, the worse you're doing. What we're doing is simply taking a squared distance from the true house selling price to the predicted house selling price, and saying if this prediction is very off, regardless of whether it's very less or very high, it's an equally bad thing. Because if it's very less, I'm not going to get the house. If it's very high, I'm going to end up overpaying drastically for the house. There are different kinds of loss functions. This was just an arbitrary choice. You will hear this explained as, oh, the squared loss is a popular loss function. We do it because there is this derivative we take that makes life easier for us. And all of these are plausible reasons. One of the things you want to think about with respect to your loss functions are you want them to be continuous and differentiable. We'll get into that again in neural networks and backpropagation, but yeah. Life gets easier if you have that, let's say, for now. So we have a loss function, and we can compare the loss of different house price predictions using this model that we have, and then update this model to reduce that loss. Update the model again, further reduce the loss. Update the model. When I say update the model, I mean the parameters, the W's and the B's, because the X's are fixed, right? You have the same data set regardless of what else you do. So all you can do is change the W's, account for features differently. Oh, if my model isn't doing well on, maybe like I'm weighting bedrooms too low, let's increase the bedroom weights. Oh, cool. Now my bedroom weights are high, but maybe my area, the area weights are not great. So I need to reorganize those things. I think that's all I want to say. So collect multiple data points to fit the parameters. Let's say we have houses sold in the last 6 months. This is called the training data. You already know this. The more training data, the better. Assume there are n examples or n samples of training data, n training points. All of these things mean the same thing. So that gives us an n dimensional vector for x, n dimensional vector for y. When I say n dimensional, I mean like n times whatever the feature dimension is. I just have n examples. Cool. So now we get to a slide that has some math. It has less math, but it has math. So what this loss function does is it takes in 4 things. It takes in your data, which is your x and your y. It takes in your weights and your biases, and it calculates a certain loss. Now your goal, sorry, I should be annotating or talk about this. So it takes in your x, your y. This is your training data. It takes in your weights and your biases, which is the parameters. How does it calculate the loss? Well, remember that we said y is equal to wx plus b. Well, now we take y minus, like get this on the other side of the equal to sign, y minus w x minus b. This is the error. And if you do this per point, then you get the pointwise error. So if you sum across all the points, and then you convert this all to these indices, wi, xi, then you get the sum of errors. But what we discussed before was we want squared errors for reasons that are mathematical, that squared errors are easier to take. Gradients of smooth, differentiable, convex, there is a certain minima. Most importantly, the convexity. I'll get to that. So we want sum of squared errors. Well, simple enough. Let's just square this. And that is exactly what is written here. So whenever you see some math, try to decompose it or build up to it. It's probably much simpler than you think. But when I was an undergrad, I used to get scared of these things. I was like, oh my God, 7 mathematical equations. I have to now sit and read them. Are you serious? And typically like in research papers, there is a certain paragraph of definitions, and then there is a whole paragraph of math. So like you forget these definitions by the time you get to the math, and then everything looks foreign and it's challenging. My advice is use a whiteboard. Write down the terms that are defined in the paper such that when you're reading a paper, you have the definitions right above you. That has helped me tremendously. But anyway, this is fairly straightforward. So this is not necessarily advice for this course, but more of like when we recommend reading some research papers to you, that's what you want to sit and do. Cool. So the goal is minimize the loss to learn the parameters. So you want to learn these optimal parameter values, W star and B star, that are minimizers or that are arguments that minimize this loss. There is a difference between argmin and min that I am not going to explain, but I will point out just so you can spend time thinking about. Arguments that minimize a loss are different. Let's since I don't have enough space to write that, let's say arguments that minimize the loss. Okay, now I can't clear it. Oh my God. Cool. So what I'm saying is arguments that minimize a certain loss are different from the minimum of this loss function. So you want to be really clear on what argmin is and what min is. Okay. Yeah. I will leave that as an exercise for you to think about, and I will move on. So far we've said that the way we train these parameters, like the optimal values that we want for the parameters are the values that are minimizing this loss that we defined as a squared error. So we made a choice of loss and we want to find the arguments with respect to that choice that minimize it. Cool. Lots of math on this slide. Again, like I said, break it down into pieces and you should be fine. The first piece that we get into is this one. So let's talk about this. Well, we're basically taking this vector norm. This indicates a vector norm. We're taking a difference. Y minus xw was the same thing we said, y minus x times w. Cool. We're taking 1 by n. So we're taking, I guess, the per sample or the average loss. Okay, so far we have that. Oh, and we mentioned above that here we've just added the weights, the bias into the weights. So we add a column of ones as the bias to start with, and then we update this to whatever value B star is learned. Right? So that's how this thing works. We start with a guess and then update it. But anyway, that's not important right now. That just means that we won't have a separate B term. For those of you wondering what happened to y minus xw minus beta, well, this B went into the W. And this x became x and 1. So that when you multiply this, it still remains xw minus beta. Right? That's it. So now we don't have to care about writing this this B separately. What this is doing is taking the partial derivative of the loss with respect to these weights. So we are saying with respect to the weights, what is the partial derivative of the loss? For a second, bear with me for a second and ignore the rest of it. In the next statement, we're saying, what if we set this partial derivative to 0? Can someone tell me what happens when you set any sort of derivative to 0? What you're trying to say? Exactly.
That it's a minima or a maximum.
Exactly. You find a particular critical point, I think is the right term. So that's all we're trying to do with respect to this loss. With respect to the weights, where is this loss minimum? So, and the value for that is this thing. Now we go back to the equation above. This is the value for that minima. We need to set this to 0 in order to discover this point. And now you see why this loss is convex is super important, because now we can simply solve this with a one-step update. So it's just solving an equation. This is called the normal form of the solution. By setting it to 0, you can see the next two steps on your own. I should clear these things. So the next two steps are this, and then finding a one-step update for this parameter. Can someone tell me why this one-step update, like, let me step back for a second. Are there any questions about this one-step update? How we got this? Oh, there is a chat. I don't know if it missed anything. How concrete is the justification that neural networks work like our brain, true local extrema? That's a great question. Partly a philosophical one, partly a mathematical one. A neuroscientist would have some thoughts. A data scientist would have some thoughts. I don't have a single answer for you. I know that a lot of people have tried to justify it. We still don't have consensus on this. So there are two sides to that argument. You can spend infinite amount of time arguing either side. The goal was to design them similar to how our brains work, but our brains have a lot more neurons than the neural networks out there. So is that really the right choice? Secondly, the question is deep learning really the right way, or should we be doing more of self-supervised learning? Seems to be the next new thing. Reinforcement learning used to be the very cool thing that like, oh, agents and simulation and, you agent learning in an environment. That is what we do. So every new topic in machine learning will have its own justification for why we are getting you closer to how biology works. And then someone comes up and throws a whole wrench in this system saying, well, but do you really want to create humans, or do you want to create things that are better than humans? So should we really be looking at humans for inspiration, or should we be thinking about more complicated things? Again, whole argument. But there is justification. The question of how concrete or is that sufficient is a whole different ballpark. Getting back to our slide right now. Loss is convex. We took the minima of that loss with respect to this parameter. So we found the value of this parameter. Can someone point out what a problem could be with this whole setup? These are great questions. X transpose X can be singular. I got one message. This is super important. I will get back to this. The other point is local minima and not global. Well, we took a loss that is convex for this reason, to avoid the local and global minima. It has a single minima. It is convex, right? So we do arrive at that global minima with this one-step update. Joseph and someone else who sent me a direct message say the same thing. X transpose X can be singular. Repeated data would make that matrix non-invertible. Cool. That's a great point. And what they are saying is, to get this to be invertible, there are some conditions you have to satisfy, which let's say they are satisfied. Again, I'm not going to argue about no correlation or whatever, but you can create a data set that satisfies this from whatever data you have. So if you examine correlations across columns, you remove correlated features, that's fine. You can arrive at this being invertible. I guess this was a biased question because I was going for a particular answer. Yeah, this question, this answer is exactly what I was asking. It would take a very long time to compute the inverse if X is a very high dimensional matrix. So sure, this is a one-step update, but matrix inversion, for those of you familiar with big O notation, is O of n cube. If this has n dimensions, then it takes cubic time to calculate this. And think about like high dimensional data that we do have in real life. We have at least like 10,000, 20,000, 30,000 dimensional data. We already discussed just this MNIST digit problem was like what, 784 times whatever number of samples you have. So and that is a black and white image of one digit. Now imagine a video of multiple high resolution frames. It's just insane. So it's clearly the mathematical solution to the problem, but not the computational solution. And for that reason, people came up with this idea of, okay, well, we don't need to find this perfect solution, but in this space, we can optimize and like create these small step parameter updates to get us to the right solution. But before that, let me step back and say, look, this was a very basic overview of how linear regression works. There are two videos in which I spend a lot of time firstly discussing basics. I don't think that's necessary for most of you. I just put that there as optional. The math and the assumptions for those of you super interested in like drilling down into this method, I would recommend the second video. This is just a reading group that we have on the weekends that we spend time studying this really amazing textbook. It's not, yeah, but it was how the TAs for this course were introduced to this, at least maybe not introduced, but refreshed this in recent times. So this is how they were taught, or more of how they taught me. But yeah, that's. I will share the slide, so you should have that, and I should clear this. Cool. Getting back to basic optimization, how are we doing on time? I think I'll spend 5 minutes. I think good. I feel like I haven't. Other TAs going to cover this in detail. Could you unmute and tell me?
Yeah, we are going to cover it in detail.
Sounds good. Then I'll spend a little time just giving you the basics, and then they can tell you what is going on. So with the loss function, we are in this particular space where every new set of W's that you give your linear model, it's going to give you new losses, right? So as you change your W's, your losses will change. The reason we assumed the squared loss was because this was a convex function and like you could optimize that. But what if it was a super complicated loss function and it was not easy to optimize? Well, it was not easy to solve in one step. Well, in that case, you take like a series of updates in the hope that you ultimately reach this point here. This point here that seems to be the minima, which corresponds to this. So this is like this thing is a contour plot of this thing, right? I don't know how familiar you are with contour plots, but they came up in geography, and hopefully you're at least aware enough. So this is the minima that you want to arrive at through this set of updates. How you determine the updates, the TAs will describe in detail, go about this algorithm, but bottom line, you ideally want to go along this path and end up here. The path is not super important. You can just take this path. In fact, this might be a better path to take if you can take that one, but in all likelihood, you're probably going to end up here. If you take how am I saying these? How am I pointing to these paths? Well, that's a great question. And like I'm thinking of this as a mountain. Okay. And if you go up a mountain and then you want to go down, you're going to go down along the slope, right? The slope is called the gradient, and going down along the slope is called gradient descent. A very, very hand wavy explanation. Like I said, the TAs will explain the math, but wherever you are on a mountain, if you are on a sled and you let go, that sled is going to take you down the shortest path to the minima. That's what you want, but you don't want to go down to the wrong minima, which was the discussion about local and global minima that someone came up with earlier. And this is the challenge, right? If there are multiple minimas, multiple slopes, which one do you go down? How do you pick the slope? How do you figure out which is the right way? Well, all of this can be done with an algorithm called gradient descent that doesn't guarantee global minima, if I'm not mistaken, but it guarantees that you will reach a minima. There are, I can't recall if there are algorithms that guarantee global minima. I don't think there is one. Like it's almost impossible to say this algorithm is always going to get you to the global minima. I think there are assumptions you have to make in order to get there, but that's what I'm going to say. This is just I want you to look at the figure here and see how W0 goes to, oops, let's clear this. W0 goes to W1 and goes to W2, which is just a series of weight updates. You'll get into the details of how you get this value and how you update those weights. That's fine. There are certain concerns you will have that again the TS will walk you through. You want to choose certain settings that allow you to go down a slope in a smooth manner as opposed to like jumping around like crazy. And then there are certain practical considerations of, well, but like, can we consider an average descent down the slope and a bunch of different things. But yeah, that's for the TAs right now. I will pause this here. I will end this the slides here and I will take your questions for the next 5 to 10 minutes, if there are any. I see a chat. We can use stochastic gradient descent to optimize it, but it might not give the most accurate result. You are right, but the entire, so this idea of stochastic, okay, firstly, what is stochastic gradient descent? I feel like I should discuss this after you've covered gradient descent for most people. I will take the next question though. If you're using a squared sum loss, then this loss function will be convex. Wouldn't this guarantee that gradient descent will be accurate measurement of true parameter values? I will rephrase that question slightly, that gradient descent will get you to the minima. I think so, yeah. For linear regression, we figured out a convex loss function should lead to global minima. But if we have deep neural networks with multiple minima, is there a way we can ensure we reach near the global minima? Near the global minima, yes, because local minimas are essentially near the global minima. But to my recollection, there is not a method that guarantees that you will reach the global minima, because if there was, then that is all that companies would be doing. They wouldn't be creating new loss functions. They wouldn't be making all of these fancy algorithms. They would just be using this algorithm that guarantees global minima and throwing as much compute at it as you need. Because no matter how complicated the problem gets, this algorithm is going to get you to the minimum. So I don't think that, like, logically speaking, this I'm explaining my thought process to you here, not giving you the answer. But logically speaking, I don't think that exists. I think it's problem specific and loss function specific. Okay, another question came in. This is related to applying transforms to features. If we have a large amount of data, then we can apply a lot of transformations and drop those which are not a good transformation. How can I go about doing this? I was thinking of using a derived inputs method using PCA. Is there a better method for this? I think that question has multiple layers. So let's boil it down first. If we have a large amount of data, then we can apply a lot of transformations. This is, I mean, you don't have to have a lot of data to apply transformations. Like if you have one column, you can transform that in multiple different ways. It's just that all of those columns are probably going to be very correlated and not reveal any new information, because you're just applying the transform, but like a function maps a set of points to another set of points, but those relationships between those points still exist. So yeah, in a sense, the question was apply transforms to multiple features and drop those that are not good. One important point that the question brought up was, yes, this can be done using PCA, but that's not, PCA doesn't tell you about the transforms. It tells you about the columns that can best explain the variance in the training set. So now again, there is an entire lecture that could be given about PCA, but because I've explained eigen decomposition, I'm going to say like this. In a sense, PCA tells you the best directions that your data is varying in. So if you have like multi-dimensional data, like 10,000 dimensions, but really like only 5 or 7 of those matter, then PCA will find those for you. So you're reducing your set of features using PCA, but it doesn't have anything to do, to my understanding, with the transforms that you should apply to these data sets. Hopefully that answered the question. There was another part to that question saying, how can I go about finding the right transforms? Well, that is a great question. I don't think I have an answer for that, but I think I know where to look for those answers. So I will post a note on CampusFire about this. I think there are some principled like there are some libraries that try a bunch of transforms for you, but that is not the answer I want to give you. That is more of like a practical perspective for this. Part of it goes back to Joseph's question about like, do you want to, if you know something about the data, that gives you a very good reason to apply this transform. Part of it goes back to the reason you apply these transforms. Again, I'll point you to a video that describes all of this in detail, just because I don't remember all of those assumptions very precisely. And there was a very good description of these things in a textbook by Shalizzi, Cosma Shalizzi. So I will post this as a note on Campus Fire. Two more questions came in. So for a loss function, I get why it has to be continuous. Could you maybe point it to the reason why it has to be differentiable and how that relates to deep neural networks? Well, we'll get into this when we get into back propagation, I think. The the simple answer to the differentiable part without ignoring the deep neural network bit is you want to find the gradient and you want to descend along the gradient. In order to find the gradient, you need it to be differentiable. If it's not differentiable, you don't have a gradient, so you can't descend anywhere. This is without having discussed like a gradient descent algorithm, but just saying like in a function, if you want to get to the minima, you go along the slope and get to the minima, right? But you have to go along the slope in order to get there. So if there is no definition of slope at a point, then where do you go from there? That is the challenge. Does normalization of data affect the rate at which we get to minima? Does it make it faster or slower? Excellent question. Typically, we normalize the data so that you don't associate a lot of, you want to scale your data, because suppose in the house pricing thing, your bedrooms vary from 3 to 7, right? But your number of windows vary from 4 to 50. And this, you don't want this to affect like the weight you place on the bedrooms versus the weight you place on the windows, because you want to express this variance as like a percentage of the total number of windows. So windows, let me reduce that even further. 5 bedrooms might be way more important than 40 windows. But because those values, like numerically, it's just 5 and it's 40, you might end up placing a higher weight on those windows than you place on those bedrooms. You don't want that to happen, so you scale that down. So you say, well, 5 out of 7 windows and 40 out of 50, 5 out of 7 bedrooms and 40 out of 50 windows. That is what you're doing by doing normalization. Sort of, again, it's S minus mean by standard deviation, which is mathematically incorrect what I said, but the sense I was trying to give you was that you're trying to normalize per feature based on the variance and mean of that feature. Hopefully, okay. Hopefully, I'm answering these questions and not just saying things that are not satisfactory. If that is the case, please post back and like force me to get to your point. Get to the point I'm trying to make for you. Okay, I'm assuming. Okay, still I didn't get it. It makes it faster to minima. Like then, how would we decide the alpha value? Again, I'm holding off on like the learning. Like there were two good questions, but I feel like it would be better for everyone that came after gradient descent. Alpha and normalization are two different things. I think alpha is what you're talking about, the learning rate. That was just like a diagram I showed you. Yeah, I really want to take these questions, but after gradient descent, because it's not helpful to the class. I'm just going to end up confusing more people before they even learn about what this alpha is. But if you want, you can make a campus wire post about this, and then I'm more than happy to like expand on like exactly what is going on, send you some links. Because this is a good question. It's just that most people aren't going to get it, and I don't want to end up confusing them. I think I get your question now. Okay. Good. What is another possible loss function here? Great question. You can take the mean absolute error. We took the mean squared error. You can just take y true minus y predicted. That's it. That is also a loss function. You can take y true minus y predicted cube. That is also a loss function. We just take the squared error because it's convenient in a lot of senses. It's convex and it's useful. But there are other loss functions out there. You can define your own. You can say y true squared minus y predicted cubed or something of that sort. Okay, another question. I was reading about Lasso, and there they consider absolute error. So Lasso is some mean absolute error. Also in their loss, wouldn't that be non-differentiable? That's a great point. There is a challenge with differentiability with the Lasso where there is a mod, and mod creates a kink at the 0. I think this warrants a longer discussion. And I will post about this on Piazza. So I have at least 2 things to post about. Let's write them down.
Swapnil,
Yeah.
regarding the normalization question, so is it like, I think earlier people used to do normalization because they wanted all the features in the dataset to be in a similar range, so that the weights assigned to every feature are same. So like if a feature, something is in the range of 10,000 and another thing is in the range of 0 to 10, then the 10,000s one doesn't get unnecessarily increased weight. So that's
Yep.
why we do normalization. I think that's what he was asking.
I thought he was asking about, does that make it faster to get to the minima? And then he mentioned learning rate. So I was like, okay, maybe I'm not getting the question correctly.
I think he was asking why we use it.
Okay. That is a good explanation then. If your house pricing is on the order of $300,000, if your rooms and windows and all of these things are on the scale of 0 to 10, and if there is a feature that is on the scale of 0 to 10,000, then your classifier is going to learn something that says, oh, the 10,000 feature has higher values, so let's just predict this using the 10,000 feature and like associate very little value to the others. So in that sense, that is not correct. So that's why we normalize the data, so that all of them are on the same 0 to 1 scale, and then you can associate weights really based on how predictive they are than just based on the scale of that feature. Lasso is non-differentiable. Yes, this is worthy of a campus wire post. Please ask me. Yeah, I will let you ask me these questions on campus wire and engage with you there. But yes, this is important. And for those of you, like, the Lasso is just like a mod, mod X. Mod X goes like negatively along the negative, or since my video is like this, it there's a positive slope along the positive axis, there's a negative slope along the negative axis. At 0, it meets in a V-shaped structure. So at 0, it is not differentiable because there are 2 different gradients at that point. So there is no defined derivative. If you post this on Campus Wire, I will actually let someone else answer it because it's a very, very common question. But yeah, if not, I will answer it. With that, I think we're over time. So I will stop here. And thank you all for the questions and attending the lecture. And we have the recitation tomorrow that will go over. Do you want to unmute and say what you are going to cover?
So yeah, we'll be starting with methods of numerical stability and hardware optimization. So looking at how floating points really work and why is it important. So I think we had a question regarding that. So we'll be going over it first. Then we'll see how the CUDA GPU works with tensors, and after that we are going to have a session on gradient descent, and along with that we'll see how linear regression actually works along with gradient descent. So I think if I miss something, Jay would be better able to explain that.
Yeah, I think that sums up like pretty well. So yeah. Sapnil,
You're on mute.
Thank you. So I will wait for your CampusWire posts, and I will see you all in my office hours this week. I will also post about that on Discord and CampusWire. I think Tuesday night India time. I will have my first office hours, and we'll have others during the week as well.